Good day, Prof. Coulter. I am Rauzuro and my student number is 219012509. I will be presenting an intelligent agent that I've developed and decided to call Solar Flare Prediction System, which will leverage feedforward neural networks. Let us quickly get an overview of what Solar Flare is all about as per the agent design that I have submit for deliverable 1. Over the years, solar flare has been defined by various studies as the large eruptions of electromagnetic radiation from the sun that can last from a few minutes and sometimes to hours. So it is a certain outburst of electromagnetic energy at the surface of the sun. Solar flares has been classified to 5 categories, which we have class 1, or should I say 5 classes, class A, B, C, M, and X. And a lot of studies have mentioned that solar flare class M and X are the most dangerous solar flare classes compared to the rest, although all the solar flare classes does cause issues. Solar flares events may cause healthy issues to uh, astronauts due to the exposure of EM radiations, and then to the life here on Earth, the life here on Earth may be affected by solar flare indirectly through the destruction of satellites, as these may cause the disruption in daily services such as GPSs, telecommunications, electrical networks, and other essential systems that depends on the satellite. So as a result, it is highly significant for us to monitor the occurrence of solar flare as well as solar flare classes, so as to provide an early warning system to the life here on Earth. So the solar flare prediction agent that I've developed seek to monitor the occurrence of solar flare events and possibly make some sort of prediction as to what solar flare classes could be possibly occurring. So this information will be useful as we will see on the interface when we go through the code. It will be useful to space astronaut decision making using the prior knowledge as to whether the space astronaut wants to go to space based on the information that from the monitoring system. So the students will then make a decision whether to go to where the satellite is located or not. So this model is going to leverage feedforward neural networks, make some predictions on the occurrence of solar flare, and then it will be using the historic data to sort of obtain its information about solar flare. It will also be able to capture the complex nonlinear relationships that is occurring between the data set, specifically the solar flare classes, which is the target variable, and the input features or the input variables, which is the other columns in the in our data set, in our historic data. Now, in that as part of the historic data, we've got the atmospheric rivers, which the NOAA defined as the regions of extratropical storms where high winds and water vapors are concentrated. This is according to NOAA. Obviously, the other part of the historic data is the event date when the solar flare occurred, the start, end, and the peak time. So all of this will be used to find the pattern that will help the agent check the relationship between the two, predict solar flare occurrence, solar classes as part of the predictions. So this information will be useful to maybe the space astronauts into checking the status of the solar flare in the space before deciding to take off. So the solar flare class is going to be our actuator, and then the atmospheric rivers, event date, start, end, and peak time will be the sensor. So the agent should be able to adapt and learn from new data from the space over the time. So this leads us to the implementation of our agent, where we will check the MLP architecture of our agent. Now, our agent was designed to follow this architecture. So on the input neurons, we've got atmospheric river, event, start, end, and peak time on layer 1, which is the input neurons, and then they're going to be subjected to weights that are stored on this edge, then gets sent to this vertex here where they're going to be subjected to ReLU. Get weights, then get weighted, added, and have the bias added to them. Well, before they are sent to the second hidden layer, and all of a sudden to the output neurons, where sigmoid value is going to be used to make the final predictions. So it is crucial for us to, when implementing the feed-forward neural networks, as part of that, we have the feed-forward propagation algorithm that will be useful for the for making sort of the predictions for both the occurrence and the class. So these are the sets of formulas. Now, this W right here is the weight, and the X is the input neuron. So this means this is going to happen. This transformation is going to happen in layer one when we are in the edge that is between layer one and the hidden layer one. So what will happen? We're going to get the dot product between all the records of our data and the corresponding weights. We add bias to that, and then we send the outcome to the second layer, which is hidden layer one, and then the second layer is going to subject that to ReLU function, store it to A1, then send it to hidden layer number two. As part of in the process of sending it, is going to weight that value that it is sending, and then add the bias to it. Then hidden layer 2 does the same, except it will be using soft plus functions, and then the weighted value in the output layer is going to be subjected to sigmoid function. So this A3 right here is going to be our predicted value. So this brings us to the backpropagation algorithms implementations. So this is very important when we are adjusting weights and biases. Which will be crucial for us to analyze the loss that is taking place. So all of these we've seen from all of these functions have been derived from this feed-forward neural networks, which aligns to this architecture of our multi-layer perceptron. So we will see how this is put in the code. So our interface that is going to make use of the predicted information looks as follows. So we're going to have an astronaut spaceships that is going to use the information, the predicted information, to decide whether to go to where the satellite denoted by S is located. Now, the space astronauts will be able to detect the solar flare event that is denoted by H, which will randomly occur in the interface. And then these stars are a representation of the space. The data that is going to be used to train the solar flare is as follows. I've taken only the first three record. Obviously, the whole data has like 12,000 something rows of data, and then as part of the columns of that data, we've got classes. As we can see, we've got class C, B, and their variations, and then we've got NOAA atmospheric river, which is in int values, and then we've got event date when the solar flare was taking place. Solar flare of this class was taking place, then the start and the peak time. So all of this is going to be used to give the agent knowledge of how solar flare takes place. So this is the perfect time for us to start going through the code. Now, what I've done in the code is that I have imported these packages. There are probably 4 more, which we will come across as we go through the code. I have import numpy library, pandas, matplotlib, scikit-learn.preprocessing, where I've only taken the labeling encoder, and in the metrics part of the scikit-learn, I've taken the accuracy to help us. The labeling encoder will help encoding the non-integer values of our of our data, and then the accuracy score is going to help check the accuracy of our models. Now let's look at the first class, the data preprocessing class, which helps to prepare our data. Now, these lines of code in this function, what we are effectively doing here, we are splitting our data into two: the training data set and the testing data set for both the target feature, which is solar flare class, and the not the target feature, but the target variables, which is the solar flare class, and the feature variables, which is the AR, event date, start, end, and peak time. So the splitting weight is that we all the training, or should I say the training data set is going to take 83% of our available data, and then the testing set is going to take the remaining 16%. And then after that, we will encode all those data. Let me scroll down. All right, this part of the code, this is where we are encoding the feature data set for training the model as well as testing the model, so as to allow our model to be able to learn from that data. The same goes to the testing and the training set of the target of the data set. So we invoke this method where we are taking those splitted class, or should I say target values of our data, and then from there we those encoded values we reshape them so that to allow flexibility, and then store them to either the X training feature and the Y training target. So this is the training data set and the for both the features and the target. Obviously, they will have same dimensions. We do the same thing to the data that we're going to use when we test our model, and then those testing data sets for both feature and target, we then store them into this reference so that we can be able to access them to other functions in the class as well as outside this class when we are training the model. Right, so this data, this arranged data, we're just putting our training and testing data sets for both target and feature variables so that we'll be able to access them when we that will be helpful when we are training our model. And then outside the class, in the same code snippet, we have the Solarflare file where we are reading from this file, CSV file, that contains this information that is displayed here when we run the code. And then from there, we create an instance of data processing where we're going to take the read event file information. From there, we then invoke the arrange data method, which is going to store the training, the training and the testing data set for features and target. And then from there, we display to see if our method is has succeeded. Now let us run, and we find that yes, it has succeeded in creating. So this add method here is just printing the first 5 values of only the first 5 values of the available record. And then we move on to the second class, the activation class, which implements various functions that will be used when we subject our, as we move from various layers of our architecture, of our MLP architecture. First is the ReLU method, which takes in the weighted input neurons, so the as we've seen from the slides, the product between the weights and the input layer where we have added the bias. We will then compare that value with 0, and then whatever it's greater is going to be returned. Now the return value in the second hidden layer will be subjected to the soft plus functions, where we're effectively subjecting that value to this function. So this equation rather, where there is x, we're going to put that value, and then the result is going to be a return here. We've even claimed the value to make sure we're vectorizing whatever result is going to be we're going to get in order to ensure stability of our method of our model. And then in the sigmoid function, this is where we're going to subject the value that we're going to receive from the hidden layer number 2, and then we subject that to these equations, and then the result is going to be we'll call it the sigmoid value, but essentially it's what the function will have predicted. Then from there, let's run this. Then from there, we move on to the loss function class, where we have implemented the loss functions. Now, the loss function is going to take the predicted value from the output layer and then make a comparison with the target data set so for the SolarFly class. After making the comparison between the predicted value and the actual value, we then subject that to this equation right here, and then return the value, the resulting value. Now this is helping us. This epsilon value is helping us stabilize our model in that sense. So let's run this and then move on to the next class, or the next class, yes, which is the feedforward neural network, which is effectively the ones which is doing the which is implementing the feedforward propagation algorithm that we have seen, the propagations of those equations that we have seen in the from the slides on part where we were presenting the feedforward propagations, the backward propagations. So this is what we're going to implement those algorithms. So the first thing that we're going to do is to generate weights and biases, the initial weights and biases, and that will be done on this special method. Now this method is going to take the input neuron, the number of input neurons, the number of hidden layers, and as well as the number of output neurons. And then from there, it will save those values in this in the reference to in the reference of this class, so that so that they will be able to access these values to other classes. So the first thing that's going to happen is that we're going to calculate the variance as part of initializing weights that will be used and biases that will be used. So we'll calculate the variance by dividing the number of output, this value right here. We're dividing them to we're dividing those values by we're dividing by those number of input neurons, and then we get the standard variations. So this dictionary here is going to store the resulting value. So this iteration is going to generate random weights and biases, and then we will store them in this part. And then we store the reference of the generated weights and biases to this reference right here. And then next is the create model. Now this create model function is what is implementing the feedforward propagations. Now the feedforward propagations, this is where we it will take the input neurons. Now in the input neurons, we will access all those weights and biases that was generated from the method above, and then we store them here, as we will make use of them as we are making a prediction. So the first thing that we're going to do, this is happening. This is involving the input layer. Now in the input layer, we will generate this matrix of data. Now this matrix of data is going to take those 12,000 rows of data with 5 columns of import variable, and then what will happen effectively is that we're going to calculate the dot product between, or should I say, the product between the weights and the inputs, and then we add bias as we've seen on the algorithms, which we store the resulting value to this created matrix. Now this values is going to be sent to the affine value. Now in the affine values is the shouldn't the affine value, but the ReLU method. The ReLU method is going to make a comparison between the weighted value with bias from the edge that is connecting the layer 1 and the hidden layer 1, input layer and the hidden layer 1, and then it sends the results to the edge where it's going to get weighted, and then have the bias multiplied to it, which is then sent to hidden layer number 2, which is going to be subjected, and in hidden layer 2, this is where the value, the resulting value, is going to be subjected. This is the weighted value of the ReLU value. So that's going to be subjected to a solar plus function, and then following edge that is connecting the output layer and the hidden layer 2. This is where the soft plus this is what's going to that soft plus value is going to be weighted, and then have a bias added to it before it's sent to the output layer. Now in the output layer, sigmoid function is going to be used to make the final predictions, and then all those values from each and every layer will be, their reference will be stored in this self reference storer, so that we can access them when we are and then when we are building, when we are implementing the backward propagation algorithm. So this sigmoid value is nothing more than it's the values that is going to be predicted. Now, when we are adjusting this build model function is going to implement the backward propagation algorithms. So it will take input neurons, which is effectively the feature variables, and then the output neurons, which is the target variable, as well as the learning rate. Now, the first thing that is going to be taken will be the input neurons, which will, the number of input neurons, which is 5 in numbers. We will calculate the gradient. So what this whole part of the function is doing is that it is implementing the gradient descent, method. So the first thing that it's going to do is that it will create the gradient by getting the difference between the forward propagation value, which is our predicted values, or should say, which is the values from the hidden layer 3, and then we have the and then the target neurons, and then use the value from the forward propagations, and then get the dot product between the two, and then divide that to make an adjustment, divided that by 5 to make weight 3 adjustment, and then do the same when making the weight base bias 3 adjustment, which is effectively just taking the sum of all the components that are found in gradient 3. And then from there, we calculate the sigmoid derivative. This will be, and then we also store the weight 3. This will be useful when we calculate gradient number 2. This will be useful for adjusting weight 2 and bias 2, which is that edge between hidden layer 1 and hidden layer 2. So we need to adjust the weights that are found there. Then we do the same thing when adjusting that we did when adjusting weight number 3, and then when we're adjusting weight 1 and base bias 1, which is the edge between the input neurons and the first hidden layer. So what happens there is that we get the dot product between the stored predicted values, not the predicted values, but rather the affine transformation values. So dot product and the transpose, as well as the output neurons, which we divide by 5. We could have just used M, and then we get the sum of the components on weight 2. The adjusted values that we have gotten there, for each case, we're going to multiply that by learning rate, then we subtract as we are doing the multiplications. We store the results to the weights bias, and then that's how we adjust our weights and bias for all those edges that are found on our that we've seen on our model or the architecture. So after doing all of that, we then start the process of training our model. Now our model, the train model function is going to take input neurons. Well, this is not an output neuron, but rather the target variable. So it's taking the training features and then the target features, epochs, and learning rate. So throughout the iteration that we're seeing here, the iterations that is taking the values of that will iterate the number of epochs time will be throughout that iterations will be storing the loss history that is taking place. So the first thing that we're going to do is that we're going to store the predicted y value that after calling the feedforward propagation algorithm method to create model. So that prediction will then be used to compute the loss by comparing the target feature, the target variables with the predicted values, and then all those loss that is being computed by this cross entropy loss will be stored in loss history. And then from there, we will adjust our weights before we make another prediction. So when adjusting our weights, we're going to use the build model. Now the build model is going to use input neurons, which is our feature variables, and then the target variables, and then the learning rate as part of that. And then from there, it then print out the loss that is computing. Plot the graph between the loss and the epochs, which leaves us to the last functions where we are making an actual prediction. Now in this part, we will invoke the create model, which is the feedforward propagation algorithms that is making a predictions. Now in that model, we are making a comparison to see if the predicted value is greater than 1 or less than 1. If it is greater than 1, then we make a prediction that solar flare is occurring, and then if it's 0, then we effectively update those values as we imply that the solar flare did not occur. So which will be the end of this feedforward neural network implementation algorithm. So let us run that, and then after running that, we move on to where we are making use of that information. So here we are going to create an instance of feedforward neural model class, and then we specify the values, and then from there we're going to train the model, and then after training the model we will train the model using the training data set of both the feature and the target variables, and then we invoke the predict method, with predicting the method from the training set, and then we store that here. We effectively just printing out what was predicted. So we check the accuracy of our predictions by comparing what the model has predicted through these informations, as well as the target training data set. And then we compute the accuracy. And then after all this is done, we're going to make use of the predicted information But first, we will check. We'll count the number of. We'll check the number of zeros and ones that were included in the prediction, in the predicted value. So what will happen is that the prediction outcome is going to check the number of solar flare occurrence and then just store them in this created variable respectively. So what is going to happen next is that I've used these packages, these libraries, to create a console environment or a console interface where we'll be visualizing our space astronauts and every other features in the interface. So we will check if the solar flare occurrence count is greater than the non-occurrence count. So if it is, then we conclude that, well, solar flare is currently occurring. We create the interface, and then these are the astronauts positions. The astronauts will be positioned initially on this part of our interface, and then the satellite will be located in this part, which is somewhere around the space. And then from there, we create the grid. As we've mentioned before, the stars, the stars will be representing the space. So what will happen here is that we're going to create 5 by 5. That's how large our space is going to be. And then we label that in the following code. So this is what we will be putting in our grid, the 5 by 5 grid that we've created. Now in position A, we have the astronaut spaceships, and then in position S is the satellite, and then this is represented or denoted by H is the solar flare that will be randomly appearing here or there. Then from there, we're going to create the space. Now, when creating the space, this is where we're going to add everything that we put, whether we stored on the grid, the astronaut spaceship, and everything that is taking place on this part of the code. And then from there, what will happen is that we defined the move astronaut function, which will be moving our astronaut between diagonally in our interface. So we check if the astronaut has not yet reached where the satellite is. Otherwise, as we are keeping track of that, we're going to randomly generating a value that will decide when the solar flare is going to be taking place, and then the agent will make use of the information it learned to sort of try to predict and as well as make some sort of observation as to whether the solar flare is taking place. So this part of the code right here, if the random value is equal to 0, then that means there is no solar flare that is taking place, so the astronaut can just move freely without any sort of problem. So there's nothing that is going to be detected there. So as we see, this is updating the position of the astronaut. And then if random value is going to be equal to 1, and then we see that especially if the astronaut is close by, then the astronaut should make use of the information it has learned to sort of try and update its position to make sure that it does not go to where the solar flare is taking place. And here we see the solar flare, and then depending on well, the prediction the agent is going to be making, that will determine the movement of the astronaut spaceship, which is our agent. And then from there, this part of the code is very important. So this will just updating our environment after every 2000 milliseconds. I know I said it was supposed to be 2000. Then from there, we invoke the move astronaut method, and then we create our console user interface. So if the solar flare obviously is not taking place, then will be checked via this part of the code, which we are effectively doing the same thing, creating a console interface for that case, moving the positioning the astronaut position. So this effectively does the same thing as the code that we have uh, on the if statement. So what we're going to do is that we're going to run this part of the code to visualize our interface. So let's see if it's running. Yeah, it's running. So there is our interface appearing. Let me quickly share that. All right, so this is our interface, but then again, by the time I shared this, it was already over. So I'm just gonna rerun it again, hopefully quick this time. Let me return to the code, and let me increase the number of the time that this will update, so as to allow us to visualize the movement of our astronaut spaceship. I'll also do the same just in case if this case gets red. All right. Then from there, let's quickly share that. Okay, this is not the right one. Okay, let's quickly share this one. All right. All right, so this is the case. This is our astronaut. So the astronaut, it's in this position, trying to detect if, let's check our, this is the result of the loss functions. Right, and then the predicted accuracy. But before that, all right. So what happened there is that our astronaut uh, was making a prediction, sort of check if solar flare is happening, and then when the astronaut identified that the sort of flare is not taking place, then it just moved to where the satellite really is. So let's rerun again. Let me share the code one more time. So what happened there is that our code is computed the loss functions. So yeah, then this is the graph that it displayed, loss over the epoch. So when training the model, this was the loss the loss first skyrocketed the value that is above 2000 until it returned back and then stabilizes. These are the predictions. So we saw that one means that solar flare is currently occurring, and then our agent acted based on that information. And then this accuracy prediction was 99.83. So let's rerun. Let me end this and let's rerun. I'll try my best to sort of. All right. For some reason it's I was late again. Let me rerun again. All right, let me quickly share. So yeah, this is our astronaut observing the environment and checking if there's any issues that is taking place, and then if there's no solar flare, then it continues to move to where the satellite is. Let me stop sharing, but rather let me go back to the code so that we can rerun again. Right, let me share. All right, so when it gets to this position, it notices that solar flare is currently taking place, and then it stops the agent. Then, as soon as the solar flare disappears, it then continues to the agent then continues to move where the satellite really is. So, what happened is that the astronaut spaceship made use of the prediction information that it obtained to sort of try to identify if there's solar flare is taking place. If solar flare is taking place, then it stops the spaceships, wait until the solar flare events is over, then proceed to move where where the satellite is located. All right, let's now Let's now return back to the code. This is we made a prediction. This is what we made a prediction here using the training data set. Now let us use the other set, the testing set. Let's test our model to see how it will behave. All right, I've run the code. Let me share this. So our astronaut initially picked up that solar flare is taking place, and then it stops, and then it did that again. It stops when it observed that solar flare was taking place, and then it waits until solar flare disappears, and then it moves towards where the satellite is located. Unfortunately, in this case, solar flare, as we've mentioned, can be quite powerful. So solar flare did destroy the satellite. So when the astronaut spaceship gets to where the satellite is, then it found that there was nothing, which is effectively the end of this interface. All right, thank you so much uh, for this. I will end the presentation here.